So I've been at work she's doing a lot of time. That's like
Right? So remember, logs are related to exponents. They are the inverse. Okay? And way back in grade 9, we learned 3 exponent laws. The product law, when you multiply 2 powers, base stays the same, add the exponents. The quotient law or division law, when you divide 2 powers, base stays the same, you subtract the exponents. And power of a power, when you raise 1 power to another, base stays the same, multiply the exponents. There are similar log laws, and you will always get these. These will be on a formula sheet, okay? And on the last page of this lesson, there's a proof of the 3 log laws, but we're not really going to go through that. Just know that in the product law, when we multiply 2 powers, base stays the same, add the exponents. When we take the log of 2 expressions getting multiplied, that's the same as the log same base of the first one plus the log of the same base of the second one. Okay? Or you can write it the other way around. So if you've got log, say for example, don't write this down because I'm not actually going to put this example in here. Like if I put log 4, 9 times 5, that's the same as log base 4 of 9 plus log base 4 of 5. Okay? Or like I said, it works the other way around. If I'm adding 2 logs with the same base, I can combine it into a single log, same base, multiplying the 2 arguments. Okay? So as an example, oh no, I did use that as an example. Sorry. Anyway, I was going to do it the other way around. So log, let's do this. Log base 6 of 9 times 4. Because if I'm adding 2 logs with the same base, I can write it as a single log by multiplying the 9 and 4. Okay? Well, what is 9 times 4? And what is log base 6 of 36? 2, right? Because remember, we're asking ourselves 6 to the what is 36. So it equals 2. When we take the log of 2 expressions being divided, that's the same as writing it out as the log of the first one, same base, minus the log of the second, same base. Or the other way around. If I'm subtracting 2 logs with the same base, I can write it as a single log by dividing the 2 arguments. So how could I write this as a single log? Log 2, 48 divide 3, which is the same as log 2 shot, 16. And what is log base 2 of 16? Well, 2 to the what is 16? 4. And finally, the power of a power, log law. If we are taking the log of something raised to some exponent, I can take that, it's the same as taking that exponent and putting it in front of the log and multiplying it. Okay? So it turns into a multiplication. So to write this as a log, I take the exponent in the argument and put it in front of the log. Like that. And now I can actually evaluate this. What is this? 2, right? The 7 squared is 49. So 5 times 2 gives us 10. But like I said, you will be given these all the time. You just have to know how to use them. Now, not only can we use the log laws to evaluate logs, but we can also use them to simplify or expand logs. And we may have to use more than one exponent law. Think about it this way. Okay? First thing I'm going to do, if there's any numbers in front of the logs, I have to use this law. In this expression, do you see any numbers in front?
Yes.
Here. How can I change this? This is the same as log base 9 of x squared. Okay, so that's the first thing. I don't have to touch the rest of them yet. So I had to use the power of a power log law. Now, think of it this way. If, like we're going to do some, remember, adding logs turns into a multiplication, subtraction turns into a division, right? So think of it this way. If I've got positives in front of the logs, they're going to be in the numerator of the fraction getting multiplied. If I've got a minus in front of the log, it's getting divided, isn't it? So it goes down into the denominator. So I can look at this and say, okay, I can combine these two. The log base 9 x squared y. And I can divide by this because it's subtraction. So this goes in the denominator. So that's what it would look like. So you've taken an expanded log expression, used the log laws to write a single one. You'd leave it like that, yeah. Because there's nowhere you can go unless you know what x, y, and z are. So when you simplify, do this law first, and then do the product and quotient ones together next. So what would we do first here? Yeah, these have to go, both of them have to go there. So this becomes log base 3 of a to the 1/2 minus log base 3 of b to the 3rd. Well, now there's only subtraction left. So subtraction turns into a division when I write it as a single log. So it's log, base stays the same, a to the 1/2, b to the 3rd. Or, what's another way to say a to the 1/2? Yeah. Okay. So again, think of it like when we're using pluses and minuses, well, we assume there's a plus in front, so that's going to stay in the numerator when I write it as a single log. This has got a minus in front, it's going in the denominator. Okay. Try this one. Remember, address any numbers in front first. There, there, there. So any numbers in front become exponents using the power of a power log law. What's the base on this, by the way? Yeah, too strong. So that becomes log W squared. I don't have to change the second term because there's no number in front. This becomes log y to the third. And the last one becomes what? Log z to the 1/2. Now all I've got are pluses and minuses left. So I'm going to write this as a single log. And I'm going to remind myself, well, this has got a plus in front, so it's going to stay up top. This has got a minus, so it's getting divided. It's going into the denominator. So is this one. But this has got a plus in front, so it's staying here. They're staying in the numerator. So W squared is up top. So is Z to the 1/2. And on the bottom is X, Y to the 1/3. You could change the fraction exponents to roots. Okay, but I would also, I would accept this. But if you also wrote W squared square root Z over X times cube root Y, that's also correct. Last one we're going to look at. It's pretty straightforward. Well, there's no numbers in front, so I don't have to worry about those. So when I combine these, what does it look like? What do I do with these? Right, I multiply them, right? So x squared times x, or x to the first, is x cubed. Now, we're going to talk about this more when we get into log equations, but there are certain values that this can be, and there are certain values it cannot be. It can never be a negative number, okay? And it can never be 0. Because 7 to the what gives me a negative number? Nothing. 7 squared is 49. 7 to the first is 7. 7 to the 0 is 1. Okay, I can never get lower than 1, an answer, or sorry, I can, they're fractions. 7 to the negative 1 is 1/7. 7 to the negative 2 is 1/49. But I'll never get to 0 or negatives. So when you're asked to state the restrictions on the variable, x has to be greater than 0. Okay, not greater than or equal to, greater than. But we'll talk about that more later on. Okay. So these examples, we were given it in expanded form, we need a single log. Now we're going the other way. So we are basically doing the reverse of these. So when I look at questions like this, I've got to write this out. Well, it's going to be log base 5 of A and log base 5 of B to the 4th. What sign goes between them? Minus. So I've expanded it out, but can I go even further? Yes, remember when we were doing previous examples, the exponents and the arguments were in front. I have to put any exponents in front. So I get log 5a minus 4 log 5b. How would I separate this out to start with? Log ax plus log a square root y minus, right. Now, any exponents have to be put in front, but you got to be careful here. This is actually an exponent, isn't it? This is y to the 1/2. So you do have to dress the square root here. So this would become plus 1/2 log base a of y, not root y, because the root becomes 1/2. Minus what? 2 log az. These are pretty straightforward once you get the hang of it. Right? How would we expand this one? Yeah, it's base 10, but we don't have to write it. W to the 3rd plus log x minus log, and y minus 1 has to stay together. So what do we use to keep it together? Parentheses. So you don't need the parentheses around these because these are just single terms. But if there's more than one term, you need parentheses. And then any exponents get dropped in front. Well, the only exponent is this one. Log. Oh my God. Log W plus log X minus log Y minus 1. Okay. Let's have a look at these ones. We are asked to write these as single logs and then find the actual value. And remember, these are on calculator. How would I write this as a single log? Log base 4. And what do I do with the numbers? Multiply. And now I ask myself, 4 to the what is 64? Great. 4 times 4 times 4 is 64. How would I write this as a single log? Log base 3. Or 90 divided 10, which is 9, yes. 2. Because 3 squared is 9. How about this one? Log, yeah, 4 times 5 divided 2, which is log 10. Remember what the base is?
10, so I'm asking myself 10 to the what is 10? 1. Okay. This one, what are you going to do first? I got to move these. So that's going to become log base 6 of 12 squared minus log base 6 of 16 to the 1/2. Well, what is 12 squared? 144. Minus, what is 16 to the 1/2? 4, because it's square root. And then I can write this as a single log using division. And what is 144 divide 4?
Well, what's half of 144? What's half of 144? 72. Now half again. Right.
That's how you divide 4. Take half again.
I heard a little frustration there. All I heard was the ugh.
Equals?
2. Okay. Okay.
Last thing we're going to look at,
You can actually do the log of any number on your calculator. Right? Remember what I said on your calculator. You've got the log button. Okay.
do log 10. Yeah, makes sense, doesn't it? You should get 1.
Because 10 to the first is 10. What do you think log 100 would be? Before you do it on your calculator, 2, because 10 squared is 100. And if you do it, you get 2. Okay? But how would I do ones like this? It's not base 10, not base 10, not base 10. There is a way we can do it, and it's called the change of base theorem. If you've got the log base A of some number, it's the same as the taking log of that number, divide the log of the base. And you can use any base you want. So what base are we going to use? 10. So like, for example, let's say I wanted to do, let's do this. I can't do this on my calculator, can I? Because it's base 10. But try on your calculator, log 36 divide log 6. You should get this. Okay? Try log 64 divide log 4. You should get this. So that's a quick way to do any log on your calculator. You're not going to get whole numbers all the time. In fact, you're going to get decimals more than you'll get whole numbers. But all you have to do is say, okay, that's the same as log 3 divide log 2. And I can use base 10. And if you do that on your calculator, log 3 divides, watch out for parentheses on your calculator, divide log 2, oops, log 3, divide log 2, 1.585, or sorry, 1.59, because it says 2 decimal places. This one, we were just doing log 785 divide log 5. And once you do it on your calculator and round it, you get approximately 4.14. This, remember, we can't combine these. Why can't we combine these into a multiplication? Bases are different. So I'm going to have to do each one using a calculator separately. Log 8 divide log 3 plus log 7 divided by log 4. Get those two answers, add them together. And it works out to approximately 3.30. Want to check if Davis clothes are dry yet?
I said a kind of regular.
This one we could combine. What would it be? What would I do? 6 divide 3 times 2. So it would be this. Okay? And that would give us log 4 divide log 7, because we can't do this one mentally. And that will give us approximately 0.71. Okay? Those are all the proofs. We're not doing that. Those are all the proofs. Okay? So, just to wrap this up, what do we do to change a base theorem for? So we can change it into a division where both of the logs are base 10, which allows us to use our calculator. Just wanted to add that. Like I said, the last page are just the proofs of everything we did today. Okay? Yes.
Wait, what? It's 7 and oh. I didn't know.
So